Bon, je suis très heureux que nous accueillons au séminaire du LINX Michele Wiggers de Telecom Paris. Michele est très active en théorie de l'information depuis très longtemps, dès sa thèse même. Elle est active dans tout un ensemble de domaines et aujourd'hui, elle va nous parler de détection distribuée dans le régime low power, alors à faible énergie.
Oui.
Michele, merci.
Donc, merci beaucoup et merci beaucoup pour cette invitation. Un plaisir pour moi de donner cet exposé. Oui, en fait, j'allais switcher. OK, so let me talk in English. I'll prepare the talk in English. Yeah, it's correct. So I work in various areas of information theory. So this is a topic that has been keeping me kind of busy this year. So you'll see most of the references of my own work are actually from this year. I guess some actually should be from next year, but I wouldn't want to put the references 2026. So it's some are more outlook. I mean, we have the results, but they have not published yet. And so there, we have obtained them with my PhD students. And so there's Cécile Bouet, my former PhD student, Abdelaziz Bounar, Nicolas Le Guic, Ismaila Salia Adamou, and Mireille, my collaborator, Mireille Sarkis from Telecom Suite Paris. And I chose this topic because it allows me to explain the results and also give a bit of an insight how we use information theory to obtain these results. I mean, many of the proofs are actually too technical to be presented here, but still, I think this is a good topic to give you an outlook of what are the tools that we use. And so maybe it can be of interest to you. Good. So, okay, so now I think, so I have a few more motivation slides. So with lots of pictures. So currently there's a lot of activity in having distributed sensor networks. And so I'm going to talk about multiple applications, and they'll allow me to also talk a bit about the challenges and why I'm interested in this low power regime, or also I should have maybe also sometimes actually low power can also, it relates to how much communication resources you have compared to the data. So actually low power in some sense is also synonym for high dimensional data, okay? So you have the distributed detection of systems with high dimensional data and limited communication resources. And of course, if you want, like, so we want to have distributed detection systems. I just reviewed some research proposals for Nordic countries. So think about Finland, about Norway with very huge forests, and they need fire alert systems. And they want to put sensors on some of these trees, and they should detect fires or not. Of course, these sensors, they need to last for very, very long because these are very inaccessible places. Not only fire, some things are also like vermin alerts, whether you need to take action on these woods or not. Okay, so this is one example why the batteries of the sensor need to last for very, very long. We've been talking about these low battery sensor networks for actually a lot of time, like for 10 years. I think now they're getting more and more into practice. So in other applications is more local, like for agriculture applications. So we want to take measurements, and then based on these distributed measurements, we'd like to decide on how much fertilizer we have to administrate, or like whether we need to raise pollution alerts and so on. Again, we don't want to change these batteries very often, and we don't want to use too much communication resources. So it's a very common theme. We have very limited batteries. And I think this is another very a typical example, these tsunami alert systems. So apparently, I've seen many of these various proposals for tsunami alert systems where they want to put sensors on the ground, on the maritime ground. That's clear. You cannot act on these sensors very often. Okay, so batteries need to last for very long, and still they have they have to communicate until the surface. Okay, so they need some power. They cannot communicate too often. Okay, so tsunami alert system, again, batteries need to last very long. We have very limited communications. And so I also show various alert systems because this is the topic I'm going to talk about, detection. I'm going to talk about alert systems. So there's a normal situation and there's a alert situation, and someone will have to take a decision whether to raise a tsunami alert or not. And often it's actually not the thing there on the ground, but it's the station there on the ground of the ocean, but it's the station there on land. Okay, so it's a distributed detection of raising alert or not. And so very recently also these body wireless area networks, people talk about them, so they want to start implementing them, and partly they've already been implemented. Okay, so I think there are various applications. So of course, they're all body area networks where we have the sensors on our skins or our wearable watches. That's the easier part. The most complicated part when you have to implant them in your body. And here I showed 3 examples. One is in the ear. So here the sensor, this like that. I think, I'm sorry for the bad quality here. So here we have implantable microphones, and they were going to communicate because the actual actuator is here close and should produce a signal to that can afterwards be processed by the brain. So this is like for people who cannot, like as hearing aids, but implantable hearing aids. Okay, so here we have the sensor, the microphone inside, implanted into the body. And here we have an implant into the heart. And so here it's a mechanism that can detect where the heart is pumping or how much is pumping or not. And this is a third example where actually it measures here inside the force that pushes on the bones. Okay, so this can, for example, be helpful for like sports applications and so on. Again, here, I mean, like you don't want to open up people very often. So they need to last for very long, these batteries. And so now in all these examples, you had very low battery. So energy consumption is a critical issue. In the next example, it's more like the data is very high dimensional. So we have images as data, but then you can now like sending images takes lots of bandwidth, okay? So again, we don't want to consume so much bandwidth. So communication is limited, maybe not only because of battery consideration, not only also, but also because it's limited compared to the huge amount of data that you want to send. Okay, and so here you can, satellite communication is currently also a very hot topic because like we are moving away from this geo-orbit satellites, these big satellites that are very far from Earth, closer like to LEO satellites, smaller satellites that are closer to Earth, and we want to produce many of them, and they should help us with new applications, like even for traffic surveillance and so on. Not only like for macroscopic imaging, but even for like very small, like detecting small events like traffics or surveillance on Earth, like navigation or security. Okay, and so as I said, here we have more high dimensional data and still limited communications. Energy is always an issue in satellites. Then we have all this surveillance of construction sites or of infrastructure. So we have drones or constructions. Here it's underground, or like we want to surveil this bridge. Okay, again, so we have images. These are cameras. They produce very high dimensional data, and same for traffic lights. Okay, it's always like there are many applications of like we have high dimensional data and we have limited communication because otherwise it's going to saturate our communication networks. And so this is basically my last example on this introduction. I want to mention it because part of the very last part of my talk is going to be related to security. Okay, so here the idea is that this is the pictures I found. So here you have very small sensors and you would want to put them somewhere for espionage purposes. Okay, so the idea is that actually people cannot detect them. So of course, people should not be able to physically detect these devices, but people should also not be able to detect that communication is going on. Okay, and so these are like some small examples. Another use case could actually be a military use case, where you have like sensors in a foreign country. So you maybe want to detect whether troops are moving or coming or some other events, but then you should not like the communication should not reveal the presence of these sensors. So here communication is not only limited because of power, but because it should not reveal the presence of the application or of these sensors. Okay, so it's actually a very stringent communication environment. Okay, so these are the three things we're going to look at: limited power, high dimensional data, and then security considerations. So communication should not be detected by adversaries. And so this is the last example before we get more technical. And here, so I put this just like to explain to everyone. So even people who maybe are not familiar with this topic of detection, what it is about. Okay, I think nowadays with learning, maybe that's less of a problem. Okay, so here the example we have, assume that on the roadside you have sensors and they want to measure, for example, traffic and so on. And smart cars also have sensors and they measure similar or road conditions. Let's say they measure road conditions or sense road conditions. Okay, so both have data. And actually, what the purpose now is of the communication is to check whether the system is working or not. So if the system is working, the car and the roadside sensor should have correlated observation. I mean, they're sensing the same road, the same weather conditions, and so on. Okay, if one of the sensors is broken, then they're going to be independent. So this is an example where actually one by itself cannot really determine whether their system is working or both systems are working or not, but jointly, by comparing their observations, they can actually decide whether the system is working or not. Okay, so in distributed detection, what we have, each one has, so we have multiple nodes, each one has observations, and we want to understand based on these observations, what is the underlying distributions? So are they correlated or are they independent? Okay, so you have data, but we don't, so we have observations, but we don't want to detect the data, we want to detect the underlying distribution. So this is like in machine learning, that's why I said it's easier now. You have the data and you want to understand the model behind, okay? Here we only have two models in binary hypothesis testing, binary detection. We either have correlated or not correlated, okay? Or some distribution or a different distribution. Good. Okay, and so this is the non-distributed problem. I want to introduce this and maybe spend a few minutes, maybe 5 minutes, to talk about this, because it allows me to tell a bit how information theorists think about the problem and what are the tools that we actually are going to see they can be used to solve the things, okay? And then I go to the distributed setup. So here we have one just observation Vn, and we have two hypotheses. So this is going to be the normal situation, and this is the alert situation. So under the normal situation, the Vn, we have IID PV distributions. If you tell me that's too easy, IID distributions, I'm with you, but things get just more complicated. You can do very fancy things, non-IID things. Expressions get very ugly in information theory. So let's keep to this IID setup and then see what we can learn from it. Okay, so this is the normal distribution. We have a P distribution, and the alert situation, we have a Q distribution on the data. And based on the data Vn, we want to see whether it's 0 or 1. And of course, we have two probabilities. So 0, if you say h hat equal to 0, means, okay, everything is normal. If you say h hat equal to 1, you say, oh, there's an alert, there's a fire, and you ring an alarm. Okay, so there are two probabilities of error, or there are two errors, there's no fire, and you say fire, and there is a fire, and you say there's no fire. It's needless to say, I mean, like here in this situation, one of them is worse than the other, okay? So we should not miss the fires. I mean, we're all used to go out for non-existing fire alarms. That's not so bad, okay? But in principle, so far, we just have two hypotheses and two probabilities of error. Okay, and so let me do a quick example. And so how would we decide? So we have like the P, so the P distribution is under the normal situation, Q under the fire situation. So in the first situation, we have a Bernoulli 0.25, and in the second, the Q is Bernoulli 0.7. So what would we decide if we decide on the thing here? If we observe this data, do we think that it comes from this distribution or from this distribution? This is sec, so everyone can think. I will, yeah, the first, right? So I think, no? Yeah? Yes?
Question, do we know P and Q?
We know P and Q. That's a very good question. But you can also, and you're going to tell me, usually I don't know P and Q. Okay, that's correct. But in this situation, you think you know P and Q. What you can do, you can extend these works. And it's not so complicated, actually, when you say, I know P is from this set and Q is from this set. But they need to be somehow different. If they can be almost the same, then it's going to be complicated. Actually, then things that I'm going to present you, they fall down. They fall apart, yes.
I just have a question. The number small n is the number of sensors, or I do not remember.
No. That's a good question. So far we have one sensor,
okay,
and one decision center.
But why do you have many 0 and 1s?
Oh, because like you can sense over time, and
okay.
It's time actually.
Okay.
So you have sequences, you sense over time at the same point. That's correct.
But then why do we change why does the bit change to 0 to 1 and 1 0? What is the physics behind? Why do we have this change, in fact, in time?
Yeah, that's okay. So I guess this actually relates to the fact why is there not more memory? Okay, so there could be fluctuations. So for example, if you take like a earthquake or like or if you have a tsunami, things like they vibrate, but they're going to vibrate around a certain level. So there are changes from time to time, but you're saying there are going to be there is going to be memory. That's correct. But in this model, there's no memory. But you can do things with memory, and then I think in that example, you would just have a common ground. So this is an easy example. I guess what would make more sense is like if you had like or like temperature between 0 and 20 or 30, and then you would have like this 18.1, 80.3, 80.2, 80.0, and things like this. Okay, that could be a more realistic example. This is like a toy example, yeah.
So in this example, you would use maximum likelihood, for instance, to see this to decide whether H.
Exactly. You would do a Neiman-Pearson test.
Right.
Exactly. Yes. You look at You look at the likelihood, and then you decide on that. Okay, that's correct. Actually, it's so in the Neiman-Pearson test you have a threshold. Okay, and so the threshold will depend on where you put it.
Proportion of what?
Depending on what is your performance criterion, you put the threshold differently. That's what I wanted to say. I'm sorry. Yes, that's correct. So I'm phrasing it this way. I'm not going to talk Neiman-Pearson because in the distributed case afterwards, like analyzing Neiman-Pearson, distributed Neiman-Pearson is complicated. And what we have here is not a Neiman-Pearson, but actually you can get the same asymptotics with a non-Neiman-Pearson thing, with an information theoretic thing, that I can analyze asymptotic, like in a distributed manner. Yes.
Detection, you have to, in your detection, you have to bias you have to put more probability to the case where you do the false things to like beta n needs to be better than fn. And so how do you do this with the Neiman-Pearson test?
The Neiman-Pearson test, you look at the log likelihood,
So you don't do this.
And then you have like you have the parameter gamma, like you compare it to the thing. I can talk about this more in a sec if you want.
I think his question wasn't you want to privilege the
exactly.
the true alarm, the alarm. If there is a 5, you want to.
Yeah. So the gamma needs to be exponentially small.
Okay.
Yeah. So gamma or like large, depending. I forgot how you phrase it, but it needs to be like very, very, very small. Yes.
This may be similar to something else. In fact, here what you have is a vector of probability. The probability to have 0 or 1. You expect there are two possible
Yes.
output in terms of vector of probability, and what you observe is another vector of probability. So you can there is the notion of distinguishability between vector of probability that you can use to detect what is the one that is the closest to what you observed. And this is called the Router's distance. In fact, it is the statistical distance of Router's.
Okay, I don't know what I don't know Router's distance. I'm going to check that. So the distance measure I'm going to use is the KL divergence.
Okay.
The Kullback-Leibler divergence. Okay, and it is the Kullback-Leibler divergence, and in fact, it's not just because it's because it's the thing to look at. And I just like give me a few minutes to tell you why it is the thing. Okay. I see I'm far too easy for you guys. I'm sorry. Okay, so I think so. On this first thing, we'll say we go to the first like this distribution because we have a 4th ones and 3/4 zeros. And for this one, we have about 62% ones, so it's very close to 0.7, and we have about the rest zeros. Okay, so I would be tempted to say 1. And on this thing here, I think we have half, 50% zeros and 50% ones. And here, as you pointed out, because we have these alert situations, we don't know, I would rather say 0. Okay, but it depends on the exact performance criteria that you have. Okay, and so I want to introduce this type, and it's simply the empirical statistics frequency. If you read information theory papers, they love types. So it's a lot about types. It's a lot about types. Okay, and it's simply the empirical frequency of the symbols. So if we have this as an example, this sequence, then we have the 0 probability, like the frequency of the 0 symbol, it's a 5th. It occurs a 5th of the time. So I guess there are 10 symbols here. The 1 symbol occurs 4 times, so it's 2/5 of the time. The frequency is 2/5. And the 2 symbol also occurs 4 times, so it's 2/5. Okay, so it's the empirical frequency. And I think that's exactly what you mentioned already. And so let me just rephrase it for those who maybe did not catch it. So are we good at it? So the type tells you the frequency. This is the frequency of the 0. And this is the frequency of the 1. And I think maybe I did a mistake here. I'm really sorry for this. I think here I probably did copy paste. I wanted to have something that has this frequency. So it should have had 3/4 zeros and 1/4 ones. I'm sorry for this. And so the type is going to be equal to PV, and we say HE hat equal to 0. Okay, so let's look at the second example. That's hopefully not correct. So here, the frequencies of the two things is like 0.375 of the zeros. So many 37.5% of the symbols are zeros, and the rest are ones, of course. And then this is actually kind of close to this thing here. So we're going to say H hat equal to 1. Okay. And then here we have half zeros, half of the time we have a 0, and half of the time we have a 1. And so now, as I said, we're in between them. But you see, it's like the thing I want to pass here is look at this empirical frequency of the sequence, of the symbols in the sequence, and we compare it to the two distributions. Okay. Sure, it's obvious for many of you, and maybe less for others. And actually, the Niemann-Pearson, so the optimal decision in 3 is going to depend on the error criteria. We can either say we minimize the sum of the two error probabilities, or this is going to lead to the Chernoff exponent. Or here we can minimize the misdetection probability. So the probability of missing a fire, and you just want to make sure that like you don't have too often a fire alarm when there is no fire, okay? So this is the thing we want to do. So this is our performance criteria. And in that case, so because like we just need to make sure that often when we have no fire, we don't say fire. Actually, we are just going to say h hat equal to 0 if the type is very close to PV. It's very, very similar. In all other cases, I mean, we have a doubt, we just say fire, okay, to be on the safe side. Okay, so technically that means like we say 0 if the type is close to PV and 1 otherwise.
Fire.
Worse. Oh, sorry, okay. And as I
Je don't know what il y a un problème avec ces salles-là.
Yeah, go ahead.
The probabilities we have written are the transition probabilities or the steady state probabilities. So you can possibly the steady state probabilities might give you a better idea of the likelihood of the events or the transition probabilities in a fixed.
Yeah, I think if you want to, I mean, like if you want to extend this to processes with memory, you would look at actually two types, as we call them. So we look at consecutive pairs, and you count how many consecutive pairs are 0, 1, how many are 1, 0, how many are 0, 0, and then you compare this thing to the, I guess, the joint and the conditional probability, the product, right? And so you have two different probabilities under the two, and then you compare where you're closer. Yeah. Okay, so this is how you extend this to things with memory. First order Markov, we're still good. Afterwards, it gets complicated. I mean, it gets complicated. Yeah. Other questions? Good. So this is the distance I'm looking at. So if you have two distributions, this is the Kullback-Leibler divergence. So in the recent years, many more people know about this because it's also used often in machine learning, right? So they use it. Honestly, I'm not sure. So we use it because the reason is like, if your data is distributed according to Q, then the probability that your type is equal to P is approximately 2 to the power of minus n this divergence. So it has a very specific interpretation. And it wasn't me. It wasn't much. Thank you so much for coming back. So, okay, so here's the setup we want to consider. As I said, so this is the probability of making an alarm when there's no fire, which is small. We require it that it be smaller than epsilon. In fact, we require it smaller than epsilon asymptotically for large block length. So we look at the limit as the block length n tends to infinity. And the question is like how fast. So we know that the probability, we can make then the probability of missing a fire tending to 0 exponentially fast in the block length. So here we have exponentially fast in the block length, and we would like to maximize the theta, so the exponential decay of this probability of error, okay? So this is like, and we call for a given epsilon, so this is the constraint here in the limit, we want theta star of epsilon is the largest that we can have for this epsilon. If we optimize, largest means optimizing over this g of n, okay? If you take the best decision rule. And so this is called the Stein-error regime. It's very well known. I'm sure many of you know it. And this is the result. The largest exponent you can have is this KL divergence between PV and QV. So I went quickly on the KL divergence. It's not a real measure in the sense it's not symmetric respect to P and Q. However, it's 0 when they are equal. And it's positive when they're not equal. So strictly positive when they're not equal. So it's kind of, it can measure kind of a distance, okay? And it does not satisfy the triangle inequality neither. But so, and the way of achieving this, so what is the GN that achieves that? And this is why what I said before. So based on your VN, on your observation, you're going to calculate the type to empirical frequency, and so it's going to be, so this is my simplex, the probability simplex, it's somewhere. And if it's very, very close to PV, according to the KL divergence, it's very, very, or even according to the L1 distance, actually, if it's very, very close, then you're going to say H hat equal to 0, so you don't raise a fire alert. And in all other cases, whenever it's even far from both, you raise an alert, okay? And so this is the Stein-exponent, because the probability, if you have QV, so under H equal to 1, the data is generated according to QV to generate something that has an empirical statistics that is close to PV is actually 2 to the power of minus n times this divergence, okay? And this is why this is the good thing to look at. Okay, so this is just the Stein thing, and this is an easy way of getting it. You can also get it Newman-Pearson, but you need to choose the gamma accordingly. Okay, and so our interest is going to be on this distributed setup. So now we go to the distributed setup. So we have one sensor with the UN, and then we have this with the VN. And unfortunately, I didn't write it, but so under H equal to 0, we have a joint distribution on U and VN, so IID in time according to PUV under H0, and their IID in time according to QUV under H equal to 1. Okay, and you're again interested in the Stein exponent, so you want to maximize the exponential decay of the probability of misdetection while keeping this below a threshold. And yeah, and so here what is important, this thing here does actually not depend on the threshold epsilon. It doesn't matter whether you accept 10% of false alarm or 1% or 0.5%, you always get the same exponential decay. Good, and so we're interested in two things. So we want, when this communication, what you can communicate here is restricted in contrast to this one here. So either we're just going to send a few bits over the channel, so we'll only be allowed to send a few bits, or we can send many input symbols, but like we have a very stringent power constraint. So these are our setups, okay? And so let's start with the case when we only have one bit. So what is the optimal thing to do if you can send exactly one bit from the sensor to the decision center? And the optimal thing is that you only have one bit. So the sensor is going to make a decision. He's going to try to find what H is, whether it's 0 or 1, and then communicates this decision. So here we assume that we have an error-free bit. So we're going to have error in the noisy communication channels later on. Now for the beginning to introduce the scheme, here we can send one bit perfectly. And so, and the local decision means that it checks that its type. So the frequency of UN, if it's close to PU, it's going to say 0, and otherwise it's going to say 1. If the decision center also makes a local test on its own, if its own frequency of the VN is close to PV, and moreover, this guy sends 0, then you say 0, and otherwise you say 1. In other words, you say 0 only if this marginal frequency is close to PU, and this marginal frequency is close to PV. In all other cases, you say 1. Okay, in all other cases, you have a doubt. And what is bad here is that in principle, you should actually be able to check the joint statistics of U and V, because you want to differentiate the joint probability distribution QUV and PUV. But because you can only send one bit, there's no way to do that. And the best you can do is just like look at these marginal probabilities. Okay, so the best thing you can do if you can send one bit. And people actually showed that even if you can send many bits, but it's only a sublinear number of bits. So the number of bits you can send is not linear in n, so it's of much lower dimension than your data, then actually this first test is the optimal thing to do. So sending one bit is as good as anything else in terms of Stein exponent. You cannot improve the Stein exponent by sending something smarter. Okay, so here, what is interesting, so here you're allowed to send k of n bits. So for example, log of n bits. So what you could do, you could potentially take your data and try to describe it, compress it using a quantizer, and then send this compression information to the decision center. However, it turns out that this compression information is so bad that actually it's not going to help you improve the exponent. I don't think it's so obvious, but actually the proof is not obvious neither. So it's by Shalabi and Papamarco. It's based on blowing up lemma and some change of measure proof technique. So it requires machinery. It's not something that's trivial. Yeah.
It's stupid because you said there is what if we send like k of n new readings to the decision center?
Yes, exactly. So you could do that. You can send k of n. So if u is binary, you can simply send the first data. Okay. So actually, it could give you an improved performance, but it doesn't show in the exponential decay. Okay. It's maybe 2 to the power of minus n this theta and then minus something less than n. Okay. So you can improve, but it's not going to be exponential. So there's like a scaling thing going on here. Okay. Other questions? So no stupid questions. Yeah.
For me, it looks strange because if you have n large, then on the sensor side, you can have a very good evaluation of the probability vector.
Mm-hmm.
And the probability vector, so you can, if you have something that is log n, so you just have a rounding, but it can be good rounding in terms of probability, vector for the distribution, and so your distribution will be very close to the one that you have normally.
Actually, I think what you are telling me, you're going to describe the type. No, you're going to describe the statistical frequency. And actually, the good news for you is that this one, there's only a polynomial number of types. So the number of types of length n is only n plus 1 to the cardinality of the thing. So you don't need, you only need log of n bits, like something like log of n bits. So you can do your thing, but it's not going to help you.
That is what I don't see that.
Because basically, okay, yeah. So so maybe, yeah, it's not going to help you. That's actually what the result says. So it's not helpful. I'm sorry. So actually, maybe more helpful is the following. So with high probability, if you are under P, under H0, with very, very high probability, this frequency is going to be close to PU. Okay. And so explaining that this frequency is very close to PU only needs a single bit. And that's actually what we did.
Oh, yeah.
Actually, so what you are saying, all other information is not so interesting because, like, anyway, if it's away from PU, you would raise an alert anyway. So I don't need to look. And
this means that the sensor can take the decision somehow.
Exactly. And actually, and otherwise, like the type itself, and you have local observation, it doesn't tell you how these things are distributed. So you still cannot merge it with your own observation. Yeah, that's correct. Yes.
Question, we're like looking things when n is big, but with the low
of larger numbers.
No, you said that the sensors needed to be used as less as possible. So at the end of the day, you have n being not that big, right?
Okay, that's a good point. So basically, I guess that depends on the application. So whether actually, like, what is limited is communication, or the sensing itself. So if you say actually that the sensing itself is limited, then you will have n relate like sk, and then you can also do some analysis. It's more complicated, but results exist. Okay, and then you can do a bit more. Yeah. I'm not sure this answers your question. It's basically not a use case that I'm looking at in this talk, but people have looked at that. Yeah, good. Good. So, okay, so this is the result. It's a bit technical. You see it again, the KL divergence, and basically because it's under H1 is like the probability, like it's according to the Q. And then here are the checks you can do. You can check whether the marginal frequency of the U is equal to PU, is close to PU, or it's and at the decision center is close to PV. That's why you get this expression here. Okay, but yeah, so just like quick information. Okay, but what is I think is interesting is like 1-bit communication is enough. Okay, but let's look at this example here where we have like PUV and QUV. So in the first example, we have, so in both examples, PU is Bernoulli half, and PU and QU are Bernoulli half, PV and QV are Bernoulli half. So the marginals itself are actually the same. And so in the thing here, the scheme I described, the sensor checks the marginal distribution and the decision checks the marginal distribution. This doesn't seem very useful because it's going to be the same. We expect the same thing under both hypotheses. Okay. And indeed, if you look at this exponent here, if you have something where PU is equal to QU and PV is equal to QV, then actually this is 0. You can do the minimization, this is 0. That means that in this example here, so the QUV and PUV are different, obviously, but the marginals are the same. And then the scheme we said does not work. I mean, like does not give a positive exponent. And the result before says that you cannot have a positive exponent. The error probability cannot decay like 2 to the power of minus n theta for any positive theta. And so the question is what happens to the error probability in that case? And so one of my students was very interested in that. And actually, so Nicolas Le Guic, and he showed that the correct scaling, the optimal error, so the minimum, the best scaling you can hope for this misdetection is probability is the thing here. So it's going to decay as 2 to the power of minus, not n, but k. Okay, k times some positive exponent, and he determined what this positive exponent is. It's again some information theoretic quantity. And what is interesting here, if you look at this, so we see the correct scaling is 2 to the power of minus k something, and he determined the optimal something. And how does he achieve this scaling is maybe related to your question. You can actually just look, or like previous questions, at the first, she's nodding, at the first k of n divided by, or like by this factor here, samples. You compress them, so now you need compression, right? Because like if the number of samples is up in the same order as the number of bits you can use, then actually you go to compress that. You send this compression information. The decision center reconstructs this compressed version of the first samples of U and compares them to V. So here the W is actually the compressed version of the first samples of the U. Okay, so here you do real compression and coding. Okay, but that also means that most of the data actually cannot be exploited, and you took them for nothing. Okay, and moreover, like the scaling is much worse, so it's just in 2 to the power of minus k and not n. So the communication bottleneck here is too strong. Good. So the next thing I want to look at is like when we have like noisy channels. So not noise-free, but noisy channel from the sensor to the decision center. And here, the result is kind of a dichotomy in the Stein-exponent. So it depends on the structure of this channel. So a channel here we look at memoryless channels again. So it's just described, if I put a 0, what is the probability, the input 0 to the channel is the probability distribution of the output for each possible input symbol. So the channel is characterized by this conditional probability distribution. And there are these two examples. So we have the erasure channel. You can have bit, we like bit erasure channels, like on a single bit. I know you guys prefer the packet erasure channel, but you can do the same. It's just like you have multiple of these things, and then you have one erasure symbol. Or if you go down to physical layer, what is much more common is like binary symmetric channels. So bits get flipped with certain probability. Hopefully delta is going to be very small for a good channel, okay? And we're going to see that for these types of channels, the Stein exponent is much different from for these types of channels, okay? And so to see why this is the case, we are going to look at the erasure channels. And maybe I'm again saying something that all of you know. So in an erasure channel, so here the thing is, I want to exploit the fact that there's no, from the 1, I can never generate a 0, okay? This is what I'm going to exploit. And that means that if I want to send a single bit, this is again because so far we looked at schemes where we send a single bit, okay? And now I have to do this over a noisy channel. And so here, if I want to send a 0, I'm going to send 0, 0, 0. If I want to send a 1, I'm going to send a 1, 1, 1, 1, okay? And now I decode in the following way. So if I observe a 0, I'm going to say m hat is equal to 0. But if I don't observe a 0, then I'm going to say m hat equal to 1. So on the erasure channel, that looks a bit, I mean, it's obvious because like if I send a 0, I most likely get a 0 and I can say 0. But actually, it's possible that all inputs are going to be erased because recall that we are in a regime where we only use the channel very few times, only k times, not so very, very, very often. And so there is a chance that we get all erased. And if we get all erased here, then we're going to say 1. That's important. And if we get a 1, we also say 1. Because and if we get the important thing is like if we get a 0, then we say 0. In all other cases, we get a 1. Okay. And in this case, the probability if you send a 1 of saying 0 is equal to 0. Because if you send all 1s, then you'll never get a 0 here. So you never say 0. So this is 0. But if you send a message m equal to 0, send all 0s here, then the probability that you're going to say 1 is simply the probability there's no 0 at the output, which is delta to the power of k. Okay, that's kind of obvious. What is important is the 0 here, and this tends to 0 as k tends to infinity. And the same thing also works for the Z channel, right? So if you have something like this is a very special thing. But if you have something like this, and we do this encodings and this decision, so if I send the 1, 1, 1 sequence, I never get a 0. And so this probability stays 0. And I only get no 0 if all of them make this transition, so it's delta to the k. So what I get from this slide is that if I have something like a Z channel, and the Z channel just means like this thing here is missing. There's no probability of going from 1 to a 0. Then I can send 1 bit such that for m equal to 1, I have zero probability of error. Okay, and the other one probability of error is also very small. Okay, so this is like now my distributed setup. This is my scheme. So the sensor checks whether it's close to type PU. In that case, it's going to send all 0s. And the decision center does its local test if it's close to PV. And moreover, it checks if one of the output symbol is 0. If one of the output symbol is 0, means that we have been here. And moreover, we are here. And then it's going to say h equal to 0. In all other cases, it's going to say h equal to 1. Okay, maybe. What's important here, so this is the scheme from before. What we would like is that if pi u is close to pu and pi v is close to pv, then we say 0 and otherwise 1. And so here, what we do, we like we can almost mimic this. We can almost trick this the channel, the noisy channel, because we are going to say if at one zero symbol, if at least one zero symbol, then we are going to say h equal to 0, and otherwise we say 1. And so if we are not close to here, then we send this thing here, and we are certainly not going to say h hat equal to 0. So actually with this scheme, what happens is that we don't increase the misdetection error probability. We slightly, compared to a noiseless channel, we slightly increase the false alarm error probability, but only slightly, but not the misdetection error probability. And therefore, actually, the error exponent stays the same as before, because the misdetection error probability did not change. And you can do the same also for the Z channel. So in other words, with this scheme, what we actually managed to trick the channel, and we managed to obtain the same exponent. So this was the same exponent as we had a noiseless channel. Okay, and so this is the summary slide on this part. So if we can have only k of n channel uses, and the channel is something like a BEC or has other missing links, then we can get the same error exponent, Stein exponent, as if we had a perfect channel, so like a noise-free channel. In all other cases, actually the channel is too harmful, and we get this exponent. But this exponent means it's simply the exponent of the local decision here. Okay, so that means if you have a channel that can change any input into any output, then the best exponent you can get is with the local decision. So communication here is completely useless once you have a very noisy channel. Okay, only this, I would almost call them pathetic examples where actually one input cannot create one output. Okay, or some inputs cannot, like some outputs cannot be created from some inputs. Because if you go down to physical layer, that is not really a physical interpretation. Okay, so actually for most, I mean, physical layer, you always have a probability of getting somewhere if you do PAM or whatever signaling. Okay, so for most channels, actually, the noisiness in the channel destroys your error exponent, and you can only get the local decision here. Okay. Of course, if the local decision is non-conclusive, you can do the same question as before, and you get the same machinery that you have like 2 to the power of minus k in the order of exponent. And okay, so we see there's a dichotomy of these two things. And so we could also extend these results to the Gaussian channels and to fading channels. And actually here, the converse was not so complicated. It was just like a few elementary steps to show that you cannot do better than this local exponent here. And so maybe here an example. So we have a binary example, binary sources. And then we see that if we have like, if we want to communicate over a BSC, then the optimal exponent in n is this thing here. And so this is the local exponent of the V. And if we can communicate over a BEC, then it's actually much larger. Okay, so this is the result. And now the question is a bit, so what does it mean? Is the story ended? Because as I said, I think many channels are actually in this class that are fully connected. So all outputs can be generated from all inputs. Okay, so the result is very negative. And in particular, when the local decision at decision center is non-conclusive, you don't get exponential 2 to the power of minus n something. Okay, so fortunately, life is a bit more optimistic. So in fact, okay, so here we have extensions to the multiple access channel, but I think I'm going to skip them. And so when, in fact, so this, so you can go to other communication setups. So this is when you can use more than k channel uses. I think I lost connection. It's okay, good. So when you can use more than k channel uses. So here we go to n channel uses. However, Yeah. Okay. So there are more positive news, which I cannot tell you. I can put the slides on my website. So the idea is like, so now go to N channel users. Okay, because like saying that the sensor is power limited doesn't mean that it has to send within K channel users, right? So the K is actually determined by bandwidth. So K, the power is going to say that if you can communicate, so if you have enough bandwidth, you can communicate over N channel users, but only a few symbols. Then you can also communicate over the time, okay? So this is not going to help you if you have a stringent cost constraint. Oh, yeah, I still don't have, I don't have the slides. If at least I had the slides. Okay. Okay, yeah, good. Okay. Okay. So here, if the power that you use, the power you can use is only sublinear, you get the same result as before. So the fact that you can decide where you put your power doesn't help you. Things only change once actually you don't have to satisfy the power constraints for each data that you observe. Because like the sensor's power doesn't matter whether, because usually you have to think of this, so you send N is a block length, and then next time frame and next time frame. So it's not a problem if you use a bit more power in one time frame, if you lose less power in the next time frame. So actually the power constraint should rather be on the expectation. And once you go on expectation, actually, you can play tricks and you can improve your exponent. And in particular, yeah, so more of these things, you can actually get exponents that are, so if your channel is partially connected, same as before, but now if you're fully connected, you can better than the local exponent. So the sensor is not going to be useless anymore, and you can improve your exponent. And you even get an exponent in 2 to the power of minus n when the local decision is useless. Okay, once you expect the power constraint. Yeah.
What is the trick when you allocate more power when it's worth it? And can you? Is there intuition?
Yeah, so you just do it like this. So when you have the 0, with high probability, if under h equal to 0, you are close to here, then you send 0, and everything else actually happens with very exponentially small probability, and so you can explode your power exponentially a lot because they almost never happen. Okay, and so you can still do 0, 0, 0, and 1, 1, and the exponent is going to depend on the exact channel one. Okay, and then we can do secrecy constraints. Oui, j'ai compris. Okay. Non, en fait, le problème, c'est qu'il me...
Oui, mais moi, j'ai compris qu'il ne va pas se décaler le final de 8h30, j'ai pas envie de
Okay. Donc, je suis désolée. J'ai même... merci beaucoup pour votre attention. Ça m'a fait plaisir. And thanks also for people in the...
Donc, on pourra poser les questions.
On comprend, il n'y a pas de souci.